This unit is going to be a lot more, how do I say it? Very like formula based, like read the problem, set it up, integrate, get your answer. Read the problem, set it up, integrate, get your answer. And it is very, very repetitive. The topic that we will be covering, let me go to the calendar, is basically how we find area, volume, and arc length. We're going to start off with area. So like we already know how the definite integral is the net area from the curve to the x-axis. We're expanding that now to talk about how can we find the area between two graphs, two curves on it. And then after we do area, we get to expand it into 3 dimensions and talk about how can we find different volumes of all these irregular shapes defined by functions using calculus. Looking at the unit, it is like a quick one. Like there's honestly no point to stretch this one out. It looks like a lot of homework. Like I do have a lot of homework. But I set it up so that each homework assignment should not take you more than an hour. Like if one of those homework assignments takes you an hour, you're probably working a little bit slow, but they should be able to be like really quick and easy homework assignments. The quiz is going to be on Friday, and again, I know that feels fast, but literally this unit is the easiest one we have this semester. There'll be 2 homework assignments that will be covered on the quiz. We have homework 1 and then homework 2. Homework 3 I'm going to leave as being optional because again, this unit does get very, very repetitive very, very quickly. Almost every problem is done roughly the same way. After the quiz, we have more volumes to do, and then we will also talk about arc length, which is a BC only topic that's not covered in AB. And when I say arc length is kind of a cool topic, we'll actually be able to find the length of a graph, so like measure how long like a sine curve is or any type of curve using calculus. And then the test is going to be on the 17th. Not really going to talk about the Unit 7 tests today. I saw the few people who need to make it up. But once I do get everyone to take it and pass them out, I know the county has a deadline that recovery, and most people don't need to do recovery, but recovery is due like within 5 days before the next summative. And clearly that just doesn't work in BC calculus when we have summatives right after the other. So I'm just going to make the recovery due by the next test, and that will give you some time if it does apply to you to kind of get that done. So what we're going to go ahead and look at is area between curves. Before we start off, there are some things that you just have to know. I shared this with you in OneNote, so I'm not really going to go over it by any means. But a lot of this unit we'll do like half of it with the calculator, and we'll do the other half without a calculator. You're expected to know all your basic parent functions and basic transformations of them. So if I say something like 2 minus the square root of x, you should have like a general idea of what that graph looks like. If I say something like, I don't know, cosine of x plus 1, you should have a general idea of what that graph looks like, because we are going to have to be able to see like the regions these graphs are making. So it is a very visual unit. We'll often have to kind of see like which function is like a top function, which one's a bottom function, which one is towards the left or the right of another one. So like knowing your parent functions is going to be very important in this unit. Any function that's more complicated, you'd either have a graph provided or it would be on the calculator portion of the AP exam. So we'll kind of look at it both ways throughout this unit. A lot of the questions we'll be doing without a calculator, but there will be many that we will be doing with the calculator. So to introduce this topic, we're going to be finding the area between curves. And so this will be something like what the problem looks like. And I have like these highlight sections I'm going to kind of move around if it works out correctly. Basically the idea and what we're going to be looking at for this first topic is how do we find the area between 2 curves? Like that's what we see highlighted in the yellow. And you can kind of imagine like if I want to find what's highlighted between those 2 curves, we don't really know a formula to find the area between those 2 curves, but we do know how the definite integral works. And how does the definite integral works? Well, the definite integral is the area under a curve to the x-axis. So like the area under that red graph clearly would look something like this. But if I just want that part between the curves, I just need to subtract off the part that's going to end up underneath it. So like the idea in this, when we're trying to find the area between curves, we're going to find the area of the top function minus the area of the bottom function. And what's going to be left over is going to be the area between those two curves. So basically the bigger one minus the smaller one, and that's going to give you the area between them. So to add some numbers to this, let's go ahead and look at this first example. Here's how these questions will often be worded. We want to find the area of the region close by, and they'll give you some graphs. Sometimes they'll label the intersection points for you. Sometimes you will have to find the intersection points. Sometimes the graph won't even be provided. You'll have to kind of like draw the graph using transformations or maybe using the calculator. So looking at this one, we want to find the area of the region enclosed between those two graphs. And you can kind of see the region is what I kind of used this little yellow piece for. That is the area we want to find. We want to find the area of that shaded yellow region. Well, how are we going to find that area of the shaded region? Is we're going to think of, okay, well, I know the definite integral is the area of a curve from the curve down to the x-axis. So I can use that blue function to find this blue area. And that would be this whole piece. But then I want to take away the parts that's not included in the overlap, which is what I have from the red function. So you're going to end up subtracting that from it to give you the overall area of what's in yellow. So let's go ahead and set this up. Things that we definitely want to make sure we talk about. I know I color-coded mine, but obviously the AP exam is going to be in black and white, so you would have to make sure you recognize which function is which. This blue function I know is f of x. Besides the fact that's color-coded, it's a negative 1/2 of x squared. A negative x squared function is going to be facing downward, so I know it was a downward-facing parabola. Whereas g of x is a positive x squared, so I knew it was the upward-facing parabola. So I have this area of the blue minus the area of the red, and that's going to give me the area of the yellow. So again, this is going to be basically from unit 5, when we first learned that the definite integral was the net area under the curve. This integral is starting at -4, ending at 2. This larger one was the blue one, so that was the 8 minus 1/2 of x squared dx. And what I am subtracting from that, this area that we don't want to include, the one that I kind of did this pink shape with. It also starts at -4, ends at 2, and its net area would be that 1/6 x plus 4 squared. And then we could have found that antiderivative, like from here, this is where this chapter kind of gets just like tedious. Like we set it up, we know that's going to represent the area, find the antiderivative twice, plug in the top, minus plugging in the bottom. There are some things that we can kind of do to simplify this integral, not that it will really save that many steps with calculating it, but what we will often see, these are two integrals, so I have the area of the blue minus the area of that pink purplish color. Those integrals have the same numbers on it, so we'll often just write that as one big integral. So an equivalent answer would be from -4 to 2, this function's area minus the other function's area with respect to dx. And I'm going to be lazy and not really simplify this one, but I can easily find the antiderivative. We have 8x minus, that's x cubed, and 1/6. This next term can do u sub, but u prime is just 1. So I have 1 over, that would be x plus 4 cubed. 6 times 3 is 18. And evaluate this from 2 to -4. So again, from here, it just becomes pretty straightforward and a lot of just like punching in numbers. So we get that the actual area plugging in the top minus plugging in the bottom. And again, what does that number represent? That represents the area of the shaded region. So that's going to be the basic idea with this first topic. Like we're going to have to kind of look at functions. We're going to see where this region starts at, where this region ends at. Different ways this is asked on the AP exam. Sometimes it's nice, they just ask you to be like, hey, which of these integrals represents the area between the curves? So it's just going to ask you to set up but not evaluate the integral. Sometimes it'll be obnoxious and you actually have to go back and find what that area is. Any questions on what I've done so far? Yeah, Lynn?
Well, the one at the bottom, like, can that be an acceptable answer? Or
That would be an acceptable answer, yeah. Unless it's multiple choice and then you get to have fun simplifying it. But they wouldn't put one like that on a multiple choice section. So I said this unit is pretty like formula based. So like if I were to convert this to a formula, like we can visually see how do we get to the area between two curves is we do like some overall area and then you're going to take away a piece of it. So what's left over is the region that you're kind of looking for. And to kind of convert this into a formula, I think of it like this. I kind of think about it more in words. So that first integral kind of exactly matches that first integral I wrote, where I wrote it as two separate integrals. That second one is going to be how we more often write it. So if we're doing the area between two curves, I'm going to think of this as the integral from A to B of the top function minus the bottom function with respect to dx. Certain things I want to make sure is kind of clear when we're looking at this one. Since we are saying dx, the a and the b are going to be x values. Sometimes I see students mess up and they look at the region, they want to do like y values, but when we say dx, those numbers on the integral sign have to be in terms of x values. The top is basically going to be the top function when you're looking at the region. The bottom function is literally going to be the bottom function when you're looking at the region. A and B will always go in order. So A will be the x value where the region starts. B is going to be the x value where the region is going to end. Other things I might make a note of kind of outside the formula, and that's going to be that the area between curves is always positive. So again, you don't have to worry about like if this region is above the x-axis or below the x-axis or maybe partly above or below. Reasons why it's always positive is when you do the top minus the bottom, you're basically subtracting y values, and like even if you do like top minus the negative, it's still going to be like a positive link to basically what's happening there. But that's going to be the area that we're going to do between two curves. And yeah, so but first formula, integral from a to b, top minus bottom with respect to dx is going to be the area between two curves. So let's go ahead and look at this example. Is this one I want to do? Yeah. So we want to go ahead and find the area of this one. So I have my region shaded in purple. And I have two graphs. I know they're color coded, but again, let's make sure we recognize why I know that certain graphs go where. I know this top one was the red one because it's a downward facing parabola, so I know it should have a negative x squared in it. The blue one I knew was an upward facing parabola, which is why it had a positive x squared. There's no numbers on here, so we will have to do some work to find what numbers go in my integral sign. But again, there's always going to be two parts to your answer. You always want to show the setup, so you should have a very clear, definite integral setup. And then this one will go ahead and evaluate by hand. So you have the definite integral, then you have the antiderivative, and then plugging in top minus plugging in the bottom. So let's go ahead and start setting up the integral with what we know now. So this is going to be the integral I'm doing with respect to dx. I'll have the top function minus the bottom function. Some students like drawing like a little vertical bar just to kind of make it very, very clear to them, like which one's the top, like what's at the top of the vertical bar, what's at the bottom of the vertical bar. So if I'm looking at this one, the top function is this 4 minus 1/4 of x squared. And the bottom function is this 1/4 of x squared minus x. So we've done the first part, we've set up the integrand. We do need numbers. If it's talking about an area, we need numbers on the integral sign. So we basically want to figure out where this integral is starting at and where this integral is ending at. how are we going to find those values for this problem? How will we figure out where that region is starting and ending? Say it again.
Intersections.
They're intersections, yeah. So how do we find the intersection points? Set them equal to each other. Yeah, so go ahead and do that. So we want to figure out basically where they're starting at. They're starting and ending at their intersection points. In math, how do you find intersection points? Algebraically, you find intersection points by setting them equal to each other. We'll go ahead and say any type of equation you have ever learned how to solve can show up when you're finding intersection points. Like this is a polynomial one, could be a log equation, could be exponential, could be trig, could be rational, could be radical, I don't care. You learned a function, you know how to solve it. Probably would make some recommendations to you. Looking at this one, I see there's x squared and x's, so we are going to want to get it to equal to 0 and factor. I don't like factoring with fractions, so I'm going to go ahead and just multiply everything by 4 to basically get rid of that denominator. So I would have 16 minus x squared is equal to x squared minus 4x. Get it equal to 0. And then solve. So I'm going to go ahead and factor out that 2. So I have 2x and x, two numbers that multiply to give me -8, but add to give me -2, -4, and +2. What have we found? We now know that this graph is intersecting at 4 and -2. So graphically, this region is starting at -4 on the x-axis and ending at +4. +4, there we go. Where do those numbers go? Those numbers go on my integral sign. In order, this region starts at -2 and ends at +4. If I just ask you to set up an integral but not evaluate it, you could literally just leave your answer like that. If you did need to evaluate it, one thing I would recommend is, of course, always try to simplify it if you can. That will just make the math easier in the long run. If I was evaluating this one by hand, then I would basically distribute that negative and combine any possible like terms. So I would have 4 -1/4 x squared minus another -1/4 x squared, we -2/4, -1/2 x squared, and that will become plus x. So there's my simplified integrand. And then if I want to find the area, find the antiderivative. And then plug in the top number minus the bottom number. And then that's where this problem just gets kind of tedious. Plug in the top minus the bottom. And again, you can leave your answer like that. Again, it's important. What does that number represent? It is some number. I'm being lazy and not simplifying it, but it literally represents the area between those two curves. I do think it's nice to connect this back to Riemann sums. I know it's been a while since we looked at Riemann sums in terms of the graph, but I think it's a good visual to remind yourself where the heck this formula is kind of coming from. Where this definite integral is coming from. So when I do the top function minus the bottom function, this is like the top y coordinate minus the bottom y coordinate. So you're literally finding the height of a super skinny rectangle, if you will, the top one minus the bottom one. So basically this is like the height of a rectangle. dx is like a teeny tiny skinny width of a rectangle, or the base of it. When we did Riemann sums, base times height is the area of the rectangle. We added up a bunch of rectangles. That's what the integral sign is doing. We're just adding up an infinite number of rectangles, starting at -2 and ending at 4. And that's kind of why this is giving us the area. Any questions on that one? All right, I'm gonna skip the next one for now. We'll do it tomorrow, because I did want to spend some time with the calculator one. So this is gonna be the next one that I'm looking at. Do want to talk about the calculator for a little bit for you right now. When I do this problem, I'm going to try to do it a little bit slowly to show you all sorts of tricks that you can use in the calculator to save you some time. Honestly, I probably want to do all these tricks if I'm just doing one problem, but as this unit progresses, like we'll probably have like a question with like a part A, B, C, and D using the same region. So like kind of being able to do shortcuts will just make things a little bit shorter for you in the long run. First thing, again, using the calculator, definitely make sure you're in radians. This one has no trig, so you'll be okay if it was in degrees, but good habit just when you're in this class to make sure you're in radians. Things you want to be able to do when you look at a problem like this. Several things. We first want to know what this region looks like. Like I need to know what the top function is, I need to know what the bottom function is, so I do want to be able to graph it. I also need to figure out where this region is starting at and where this region is ending at. So I'll use my calculator to find the intersection points. And then I'll use my calculator to actually find the integral. When it comes to showing your work, officially the only work you have to show is the definite integral setup and your answer. Even on the AP exam, if they don't ask you for the definite integral, they're still expecting it. They'll still show the definite integral and then your answer. So let's go ahead and graph these. Let me switch over my screen view real fast. If you have one of the newer calculators, it's kind of nice because they will be color-coded. But again, I definitely made it through calculus with a TI-83, so you can still figure out everything without the nice colors. First off, before we graph it, I do want to show you some settings that I personally prefer to have in my calculator when I'm doing calculus. And the first one is, in like regular mode, your calculator is set to graph your functions like in order. Like it's first going to graph y1, and then it will graph y2, and then kind of keep going down the line. I know it doesn't seem like it will save so much time, but trust me, saving every second you can counts, especially in the AP exam. You can tell your calculator to graph more than one function at the same time. And how you do that is if you hit the mode, you're going to go down to, it's like, what was it, 6, 7 rows down, and you probably have sequential highlighted, and I would recommend highlighting the simultaneous one. So kind of highlight that and hit enter. That will just save you a few seconds, not many seconds, but it will save you enough where you're not being annoyed and staring at your calculator thinking. And then go ahead and graph them in your calculator. It is important to, of course, use parentheses and type them in correctly. I would definitely remember which one you put into y1 and y2, even if you have to make a little note to yourself. So I'm going to go ahead and put f of x into y1 and then g of x into y2. And my calculator screen is not sharing. Let me try that one more time. There we go. Sorry for those of you at home. Again, the setting I changed first is under mode. I changed that to simultaneous, and then I want to graph it. When it comes to graphing, Zoom 6 I always recommend hitting first, but you are going to have to get used to sometimes changing your window to better see the region. So like there's mine, like I can see the region. I am going to kind of like change my window just so I can just focus a little bit better on what I'm looking at. So I'm going to go ahead and hit window. I see this is all like in the first quadrant and pretty close to the origin. So I'm going to change my x-min to -1. And I'll change my x-min to 6. Again, this is kind of purely optional. And my y-min, I'm going to do -1 to 4, I think is what it looks like is going to fit. And then hit graph. And then I can kind of easily see the region that I'm dealing with. Now I've shown you how to find intersection points before. I'm going to kind of show you another trick of how you can actually store an intersection point in your calculator, and that will save you from having to type in 5,000 decimals each time. So how do we find intersection points? I'm going to go ahead and do second calculate, or second trace, and we're going to find an intersection point. I recommend, just so you don't accidentally set your integral backwards, to find the one you see furthest to the left first. So it's going to ask you some questions like, what's the first curve? Yes, that's my first curve. What's my second curve? Y2. Yes, that's my second curve. And then guess. Again, I want to find this first one. It's close to 0, so I'm just going to type in 0 and then hit enter. And then it will pull up the intersection point, the x and the y. One thing I want to say about this, we are going to use our calculator to find the definite integral. Yes, in calculus, we need to be exact to 3 decimal places. However, you need your final answer exact to 3 decimal places. So if you round on that integral sign, there's a big chance that your final answer is going to be incorrect. So option 1, look at that long decimal and go ahead and make a note of it on your paper. Or immediately after finding the intersection point, you're going to hit second quit to take you back to your home screen. And right now your calculator is storing the x coordinate as your intersection point. So you're going to type in the variable x, and then you're going to hit the store button, which is above on, and then pick a letter. I'm going to choose A because that's how the formula's written. So I'm going to do alpha A, and then hit enter. And now my calculator knows that the variable A is the x-intercept of the graph. So I don't have to type in that decimal in my calculator. Gonna do it again. Again, watch if you need to. So I'm gonna go back to my graph. Now I need to find the second intersection point. So I'm going to do second calculate. I want to find an intersection point, so 5. Y1 is the first curve, Y2 is the second curve. Again, I want my guess to be closer to the other intersection point. There's the second intersection point, that 2.1909685. I'm either going to write that down or save it in my calculator. How do I save it? Second quit. That x coordinate, I want it to be stored as, I'm going to hit alpha b. And now that's stored into my calculator. And so now when I do this problem, I really just want to go ahead and set it up. There we go. I'm just dragging my screens here so we have something to look at. Other things you want to make sure you do is we want to make sure we know like what's the top function and the bottom function. Maybe yours isn't color-coded, or maybe you don't remember which is which. If you just hit trace, you'll be able to see your cursor, and I can see that my y1 is the f of x. I see that that is the top function of the region we're talking about. And so g of x would be the bottom function. So if this was a question on the AP exam, what I would do to kind of set up my work, again, you do want to show your work before you get to the answer. This is going to be the integral from 0.118 to 2.199. Again, when you do those in the calculator, you're going to use more decimals than that. But if I'm just writing an answer down, what I'm writing down just needs to be exact in 3 places. The top function was this one. You can either write 10x over e to the x, or since they named it as f of x, you can just put f of x. What's the bottom function? You can either write 3/2 of x, or you can just write g of x since they named it that. Dx, and then we're just going to use our calculator to find that definite integral, because we actually can't do that one by hand. To remind you how to do that and some other shortcuts you may like to do. So again, back at my home screen, Math 9 gives me my integral. Again, type in the long decimal, as many decimals as you can fit, or I save that lower limit as a, so I'm going to go ahead and just type in alpha a. Where do I want that integral to end? You're either going to type in 2.198968478 to be exact, or I saved it as b, so I'm going to go ahead and hit alpha b. And then either type in the functions, or you can use like the y variable shortcut. So y1 was my f of x, so I'm going to hit vars, y vars. This is a function, and y1. So there's the top one minus the bottom one, vars, y vars. It's a function. Y2 is where g of x was. and all this with respect to dx, and then hit enter. So that final answer represents the exact area between those two curves. Again, many students, I know I was the same in high school, I hated using those shortcuts because I wanted to like see the functions being plugged in, and so I would type it all in. I don't know why, because then you make careless mistakes typing it in when you could just recall what's already in the calculator. If you are typing in the function and not using the y-bars shortcut, then you would just want to make sure you use parentheses correctly, especially when you're doing like minus the bottom one, making sure you group it in parentheses appropriately. So what answer am I going to write down? That is 2.959, and that's how exactly it would need to be. 2.959. Any questions on any of that? And we'll be using the calculators fairly often, so you will start getting more and more comfortable in using that calculator. But any questions on that one? All right, next one I want to do is this one. So we're just going to set this one up. We're not actually going to solve it out by hand. But so far we've only talked about how we find the area with respect to x. That's commonly what we're going to do. Like we're going to do a problem with respect to x. But technically, like we saw this in last unit, like you can take the integral with respect to t and have like dt in the problem. We've seen ones where we did it with respect to theta and had d theta in the problem. When it comes to area, we can also do the area and make a decision of whether we want to do it with respect to x or whether we want to do it with respect to y. I chose this one because we very well can do it two different ways. And I just want to kind of do this one so we can talk about like what does it mean to do it with respect to y and how would I know that it would be easier to do with respect to y. So WRT, that's just me being abbreviating with respect to x. When we're doing the integral with respect to x, we know a and b has to be x values, and it's basically the top minus the bottom with respect to dx. Now looking at this region that I have in yellow, what's kind of the issue with doing top minus the bottom of that yellow region and setting up the integral? You have two tops, right? You have this red one. So like on this side of the problem, top minus the bottom is that line minus the green function. But as you move across, it becomes the blue over the green. So the top function basically switches, not like halfway between, but somewhere in the middle of that region. How many integrals do you think you're going to have to set up? Two, right? So we're going to say, hey, here's the dividing line. To the left of that line, you have one top minus the bottom, and then to the right of it, we have another top function minus a bottom function. Here's how the AP exam will sometimes tell you to do these questions. They'll say set up, but do not evaluate. So again, your answer is just going to be the integral or integral expression. So setting it up, again, we're doing it in terms of dx. So my first region is starting at the x value of 0. 3 is where that region is stopping at. I have the top function minus the bottom one with respect to dx. Don't forget that part. And then we're adding to that, this next region is starting at 3, picking up where the other one ended, and ending at the x value of 4. Its top function is the square root of 4 minus x minus its bottom function, which is the negative 4 minus x dx. So how are we going to set up for that one? Could you do this one? Like, yes, you could find the antiderivative, making sure you do some use of, but you could easily do this one if you wanted to. Even the second integral does simplify somewhat nicely. Minus another negative makes it a plus sign, so you could have written the second integral like this when you add the square roots together. But that's how you would do that one if you were doing it with respect to x. This one to me though, if I was personally doing it, I would personally choose to do this one with respect to y instead. The reason why I would choose to do this one with respect to y is I could create and find the same area, but it wouldn't require me to do two separate integrals. So what do I mean when I'm doing an integral with respect to y? I'm just going to kind of change it so I have a little bit more room. If we're doing this with respect to y, the formula is going to be a little bit different. So instead of being the integral from top minus the bottom, it's going to be the integral from the right one minus the left one in terms of dy. If I'm doing it in terms of dy, your a and your b values now must be y values. And when I say dy, it means everything has to be in terms of y. So your functions themselves, actually I shouldn't call them functions because they may not be a function. The curves themselves, you're going to write them in the form of x equal something in terms of y. So instead of y equals and it being like something in terms of x, you want to put it into x equals, and then basically the y is going to be on the other side of the equal sign. Why to me this one is going to be easier to do in terms of y is what I have as the blue and the green graph as two square root functions. In terms of y, that's just going to become a single horizontal parabola. So let's go ahead and find everything in terms of y. I think the line is pretty easy. In terms of x, is y is equal to x minus 2. In terms of y, it's x is equal to y plus 2. Like that would still graph the same line. Both of these square root functions, so like one of them is y is equal to the square root of 4x, the other one is y is equal to the negative square root of 4 minus x. They're technically the same function, or I shouldn't say function again, the same curve. If you square both sides, you're going to end up with y squared is equal to 4 minus x. Solving for x, x is equal to 4 minus y squared. Hopefully you remember from pre-calculus. When y is squared, that's going to be a horizontal parabola instead of a vertical one. So that's kind of what the shape we're looking at. So if I want to go ahead and set up the integral for this one, we are in terms of y, so it's just going to be one integral. The right function is going to be the horizontal parabola. So the right function is going to be that 4 minus y squared. The left function is going to be the line. In terms of y would be y plus 2. We are in terms of dy. So what goes on our integral sign is going to have to be y values. So when I think about where this region is starting at, so kind of at the bottom, to where this region is ending at. Again, you want to make sure you use y values instead of x values. This appears to be starting at -2. Not appears. It is starting at -2, and it is ending at the y value of 1. This integral right here, if we were to evaluate it, would give us the exact same number as this double integral that we did on the previous slide. So you can kind of see that sometimes dy will be easier, sometimes dx will be easier. Yes, Liam?
Is there a way to do dy in your calculator, or should we just do dx?
Say it one more time.
Is there a way to do dy in your calculator, or just do dx?
Good question. So if I'm just typing this in my calculator, your calculator can only graph it in terms of y equals, so in terms of x. So like this one you could do by hand, but say I wanted to just evaluate this in my calculator, I would just type in x's because no one knows like what you're typing in your calculator. You'll still get the same answer. So like in the calculator, if you typed in 4 minus x squared minus x plus 2 dx, you'll get the same number as what that integral is. You just want to be careful, make sure you didn't write dx on your paper, it'd be great. Leave in terms of dy. Yes, sir?
Why is 4 minus y squared in the top curve?
The 4 minus y squared is the right one, because you kind of think like when we do top minus the bottom, you're thinking about like what's furthest from the x-axis, like the closer one. It's like there's the bigger x and then the smaller x. And again, think of them as like x coordinates, like we're literally finding the length of that. Like it's like an itty bitty rectangle. So if I want to know the length of it, you do like the big X minus the smaller x. So last slide I'm going to do today, right? Yeah. So I'm going to do one more slide and I'll save just the last examples for tomorrow.
Mr. Brown,
Did that? Yes, go ahead.
how would we tell if like if we should do a y with respect to y if we don't have a graph? Like,
Good question. So one, you want to have a graph. Like you have to be able to visualize these regions. So like if you don't have a graph, you need to produce one. So either it's going to be a calculator question and you're going to be able to graph it, or the graph will be provided for you, maybe not labeled, but it will be provided for you. You can still match up the functions. But this unit is like, trying to think of the read. Yeah, this unit you always want to have some sort of like sketch in front of you. Even if it's not like a perfect graph, you need to have a sketch to determine several things. So like I changed it, this is the last I will look at. So these are just clearly sketches, like there's no numbers, no graphs labeled. You want to have a sketch first off to determine, hey, is this going to be easier with respect to X or with respect to Y? And then you want to be able to have the graph in front of you to figure out is which one's the top, which one's the bottom, or which one's the right, and which one's the left. So take a moment and look at those 5 for me. Again, I took away the numbers from them. I took away the actual equations. That top row is just 2 graphs creating that yellow region. The bottom 2 have 3 graphs creating the yellow region. And I want you to look at that one and determine if it would be easier if there were numbers there. Would it be better to do with respect to X, meaning you had like a single top and a single bottom? Or would it be easier to do in terms of Y, meaning you had like the single right function and the single left function? Or would it be just as difficult no matter which one you did it? So take a moment looking at those 5. And again, you're really just determining like if you have to set those intervals, would you prefer to do it in terms of X or Y? We'll go over them, and then that's where I'm going to stop today's notes at. And often when I'm deciding whether I want to do it in terms of dx or dy, like for dx, I might draw like little vertical bars and kind of see which functions I'm connecting. If it ever switches and I would be connecting like 2 different functions, then I know that I'm going to use at least 2 integrals, or maybe dy would be easier. And then kind of opposite, that would be true if I'm doing it with respect to y. So what I mean by that, in this first one, that black line I drew kind of going up and down would be the top minus the bottom I'm doing in terms of dx. If I was doing it in terms of dy, at one point I'm connecting a blue to the red, and somewhere else I'm connecting like one side of the blue to the other side of the blue. So for that first graph, would you prefer to do it in terms of dx or dy?
Yeah.
Dx for sure. So we'd have to use one integral because that blue is always the top, that red is always the bottom. What about that second one in that first row? Would it be easier to do in terms of x or in terms of y? Y. So we're looking at that one. The top and the bottom does switch as you move across. Left and right, though, stays consistent, so dy would be best. What about that third one in the first row? Either, right? So you could use dx or dy. Some students will be like, well, which one would be easier? And there's like several things that could make it easier. Often your functions are going to be in form of y equals. So oftentimes you want to rewrite anything if it's in terms of dx already. So typically if I have a choice, I'm going to choose dx. The only time I wouldn't sometimes putting it into terms of dy might make it an easier integral. Like if it's in dx and it's a square root, dy would be like a y squared. So sometimes you can make the integral a little bit easier to find. What about that first one in the second row, dx or dy? dy. So we have the only thing that's consistent is left to right. Again, you could do it in terms of dx. You would just require two separate integrals. And then that last one, dx or dy, would be just as difficult. It would require two integrals no matter which one you were doing. Questions on those five? All right, so that's basically the notes. Like I do have a few more examples, but they really are just examples. There's nothing else new to learn. We'll go back and do that natural log one I skipped over, and then these last two examples. What I want you working on for homework tonight is that first homework number 1. Again, all these homeworks are pretty quick to do once you get the hang of it. Like you can already kind of look ahead and see that homework number 2 is literally 2 questions. Let me be honest, 2 questions, they each have 4 parts to them, so it's really 8 questions. But homework 1 is probably the longer one you see on here, only because you have to evaluate some of the problems. A lot of the ones that we'll do after the quiz will just be like, hey, set up, set up, set up, set up, which again, the AP exam does a lot of. When it comes to the quiz and the test, I'll usually have like a setup, 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 and then just evaluate only one per page. But a lot of this unit is just like, look at your graph, look at your region, set up the definite integral, and then sometimes evaluate it. Where we'll expand this is starting on Wednesday. We're going to turn area and go into 3 dimensions and start looking at volume. But again, it's going to be very formula heavy and things like that. Did add a lot of written instructions this last homework. So just follow the instructions for the most part in the book. If it tells you to just set up the integral, then don't waste your time and try to evaluate it. I do want you to do most of these by hand, just so you don't lose, like, finding the antiderivatives, and also just to practice all those parent functions and what this graph will look like. Except for, I'm okay if you use the calculator graph number 20 and 62, which I typed in there. And then I wouldn't really expect you to do the integral for 36 or 40 by hand. You can use a calculator for that. There is one that looks difficult, and I do have a reason I want you to practice it. But number 72, when you work it out, it's going to look like an ugly integral, but I do want you to do it by hand just to not forget the rule that 72 is using. But y'all can go ahead and get started on that homework. Tomorrow's notes are going to be fairly short, and you actually will have most of the period to work on that homework 1. There is a 3rd homework this week, but it is going to be entirely optional. You can kind of think of it as like a quiz review. But the only homework that I'll be collecting this week will be homeworks 1 and 2. So y'all can go ahead and get started on that. I guess you have like 7 minutes left of class, so not too much. But again, tomorrow will be more of a work day and less of a note-taking day.